Now we're going to start examining the progression of our understanding of the structure of an atom, beginning with Bohr's model, which was established in 1913. However, leading up to that, in 1885, Johann Balmer determined there was a mathematical relationship between the wavelengths and the lines in the hydrogen spectrum. And he developed an equation that predicts the four emission lines of hydrogen, or the hydrogen atom, with high accuracy. Balmer's equation inspired the Rydberg equation, which we'll see, we'll see the constant in a moment. And this in turn led physicists to find the Lyman-Paschen bracket and bracket series shown on the next slide. Bohr's model, or Bohr, used Rydberg's equation to determine the energy associated with that hydrogen atom. And in his model, then, electrons can only have specific or discrete energy levels, and electrons can transition or move from one energy level to another by either acquiring or releasing energy. And the difference in the energies of the two energy levels is designated, the energy that's either acquired or released is equal to the difference in the energies of the two levels. Each energy level is designated by a specific value of what we're going to call N, the principal energy level, or the principal quantum number. This is the equation that was used, and N in this equation, so we can calculate energy of a particular energy level or quantum number, which are whole numbers ranging from 1 to infinity, essentially. So we have a diagram of an atom, and where we have the nucleus in the center, and there's Rydberg's constant. So nucleus, and then the first energy level, or the first energy level around that, n equals 2, n equals 3. One thing I want you to note is the distance between energy levels increases as the n, or principal quantum number, gets larger. However, also what is shown here is that if an atom absorbs energy, an electron can be promoted from one energy level to another. So let's say we have an electron in n equals 2, enough energy is absorbed to kick it up to n equals 3. And when it falls back down, which we'll describe in a moment what that is called, a photon of light is emitted. So this photon is equal in energy to the energy that was absorbed. So we say that an atom is in its ground state when it's at its lowest possible state of energy and most stable. So this electron in the n equal 2 is in its ground state. When it gets promoted to n equals 3, this is the excited state. So it has higher energy than the ground state, but it can't hold on to that energy. It has to let it go. And when it does, that photon is emitted, or that packet of light. Now, this diagram shows the other series that were mentioned in the previous slide. Here's the Balmer series, which we spoke of. Notice here that the lowest n value for the Balmer series is 2. For the Lyman series, it's n equals 1. Paschen series, n equals 3. And the Brackett series, n equals 4. So if, and we see this infinity up here, if an electron gets promoted or the atom absorbs enough energy, that electron can be ejected from the atom, or it's ionized. So remember, we talked about state functions when we were discussing thermochemistry. The same applies to the energy of a photon, or the change in energy. We can calculate that using E final minus E initial. So energy is a state function. And using that Rydberg equation, E final is going to equal minus the Rydberg constant times 1 over n final squared. So n final is the final resting place, whether it's higher than n initial or lower than n initial. We can also say that E initial equals minus the Rydberg constant times 1 over n squared initial. And these can be combined, and we can utilize this equation to calculate E of a photon. So if n initial is greater than n final, a photon is emitted. And if a photon is emitted, the delta E is going to be negative because the energy, or that photon, is lost to the surroundings. Sorry. Didn't realize I needed to hit those. So let's use that equation in a calculation. So we are asked to calculate the frequency and lambda in nanometers of the emitted photon. So that means energy was released in the form of a photon when an electron drops from n equals 4 to n equals 2 in the hydrogen atom. So we use delta E, which also equals E of that photon. And I didn't show you, but I rearranged that equation so we don't have the negative. And it is 1 over n initial squared minus 1 over n final squared here. So n initial equals 4 and n final equals 2. The Rydberg constant, 2.18 times 10 to the negative 18 joules. And 1 over 4 squared minus 1 over 2 squared. And when we do that math, we get E of this photon is a negative 4.09 times 10 to the negative 19 joules. Negative because it's the emission process. If we were calculating the absorption process, the delta E would be positive. Okay. Now we're asked to calculate frequency. Frequency is always positive. We have delta E, E. Because frequency is always positive, we drop the negative given by that emission process. And we use the equation of delta E, or E of the photon, equals Planck's constant. Times frequency, which we're solving for. And rearranging and doing that division, frequency is 6.17 times 10 to the 14 s to the, minus 1. Now that we have frequency, we can solve for lambda using C equals lambda times frequency, where lambda equals C divided by frequency. Speed of light in a vacuum. And we divide that by our frequency that we just calculated, or s to the minus 1. So seconds cancel. Lambda in meters is 4.86 times 10 to the negative 7 meters, but we were asked to give frequency in nanometers, so we need to convert those meters to nanometers. So the lambda, or wavelength, in nanometers is 486 nanometers. So why is energy quantized? And de Broglie reasoned that it's because the electron has properties of both particles and waves. And he proposed that if light has both of these types of properties, that light has both, we knew that light has both of these properties, then perhaps the electron as a particle also has wave properties. So the wavelength of a moving particle can be calculated using an equation he derived from Einstein and Planck's equation. And de Broglie's equation relates wavelength to the particle's momentum. Okay? So wavelength equals Planck's constant divided by the mass of an electron in kilograms times the velocity of the particle in meters per second. Okay. So we are going to use de Broglie's equation, but just wanted to familiarize you with how that electron can exhibit both particle and wave properties. So finally, we're going to develop our understanding of the atomic structure of atoms as we understand it today. And this work was done by Schrödinger, and he developed the mathematical foundation for what is now known as quantum mechanics or wave mechanics. And he developed an equation that describes both the particle and wave nature of the electron. And the wave function describes the energy of the electron with a particular wave function, and 2, the probability of where we can find electron in three-dimensional space. Now, Bohr's model could not be applied to multi-electron systems or elements or atoms. Schrödinger's model, like Bohr's, solves exactly for the hydrogen atom, but it is a good approximation for the solutions for the multi-electron systems. So the solutions to Schrödinger's wave equation are called wave functions, and they describe how the matter wave of an electron varies with location and time around the nucleus. Essentially, these solutions define energy levels of the hydrogen atom. The square of the wave function defines what we call an orbital, and that is the space around the nucleus in an atom where the probability of finding an electron is high. So orbitals are three-dimensional regions in space. They have distinctive shapes, orientations, and average distances from the nucleus. And each of these orbitals is a solution to the wave equation and can be identified by a unique combination of integers that we are going to call quantum numbers. And we're going to introduce those now. So the first quantum number is the same one identified by or proposed by Bohr. And this is the principal quantum number n, or the principal energy level, or the principal shell. And this number ranges from n equals 1, whole numbers, and they're all positive integers. And, oops, here we go. What this describes is the energy of the electrons in this principal shell and the distance of those electrons from the nucleus of the atom. Orbitals with the same value of n are said to be in the same shell. Okay? The principal shell, or the main energy levels. The higher the n value, the greater the energy and the greater the distance from the nucleus. And as you can see in this description, we're going to see that this S describes an orbital that can only hold 2 electrons. But you see as the n number increases, or the principal shell gets further from the nucleus, the size of that orbital increases. The second quantum number is designated by the letter L, and it is called the angular momentum quantum number. And you need to know the names of these quantum numbers and what they describe. So L for a given value of n ranges from 0 to n minus 1. And you could also think of this as being a subshell. So we have the principal shell, and now we have a subshell. But what it describes is the shape. I'm sorry, I thought I was going to get that first. The shape or the volume of space that the electrons occupy. So if n equals 1, L equals 0. And if L equals 0, we're in an s orbital. If n equals 2, L can equal 0 to n minus 1, so 0 or 1. If it is 0, it's the s orbital. If L is 1, we're in a p orbital. If n equals 3, L can equal 0 to n minus 1, or 0, 1, or 2. If L is 2, we're in a d orbital. And if we went up to n equals 4, the values for L would range from 0 to 3. And when L equals 3, we're in an f orbital. So this secondary quantum number indicates the shape of the orbital or the geometry of that orbital within the subshell. Orbitals with the same values of n and L are in the same subshell. So when L equals 0, we have s orbitals, as we just saw, and these orbitals are spherical, okay, in shape. There are only two shapes you're going to have to know, and this is one of them. If L equals 1, we're in a p orbital. And these are, you could describe them in a couple of different ways. Peanut-shaped, barbells, or dumbbells. But when we have L equals 0 and we have an s orbital, there's only one of those orbitals. When we have L equals 1 and we have p orbitals, we have 3 different orbitals, okay? And they are oriented on an x, y, z axis. So 3 p orbitals. Okay? If L equals 2, we have d orbitals. And as you can see, these are a bit more complex. Thought I had, well, there it is. These are, 4 of them are like clover leaves, and you don't need to remember these. But notice that they are all oriented differently along these axes. And then this one is the only one shaped like this. It's kind of like the P, but it's got a donut around the middle here. Okay. The F orbitals are even more complex. So there are 5 d orbitals in the L equals 2 subshell. Okay. The third quantum number, designated by m sub L, is the magnetic quantum number, or m sub L. And this gives the orientation of an orbital in space around the nucleus. We just saw the shapes are designated by L. M sub L is describing their orientation around the nucleus on that XYZ axis. And it also divides the subshell into the individual orbitals. So for a given value of L, M sub L ranges from minus L to plus L, always centered at 0. Okay? So if L equals 1, where we're in a p orbital, M sub L ranges from minus 1 to plus 1. These are the 3p orbitals. If L equals 2, M sub L ranges from minus L to plus L, or minus 2 to plus 2. And this is the 5d orbitals. Okay. So M sub L, or the magnetic quantum number, describes the orientation of that orbital in space. The final quantum number is not attributed to Schrodinger's wave equation. The first three are. But what M sub S designates is the spin, or describes, of the electron. And it's called the spin quantum number. It has one of two values, either plus 1/2 or minus 1/2. So this was discovered by a pair of graduate students. And what we didn't perhaps see in the hydrogen emission spectrum was that hydrogen actually has a pair of red lines at about 656 nanometers, where Balmer thought there was only one. And other pairs of lines were discovered in the emission spectra of other multi-electron atoms with a single electron in the outermost shell. And a pair of grad students proposed these doublets could result if the electron were assumed to spin in one of two directions, producing two energy states not accounted for by Schrodinger's equation. And that's exactly what happens. So it demonstrates, oh, and actually the work that they did, oh, sorry, here. It's here. There. This is their experimental setup for this work, where they have an oven, they're heating these atoms up, there's a slit in the screen, so there's a beam coming out of here. These are electrons, so they're exciting these atoms. And there are magnets and a detecting screen. And depending upon the spin of that electron, it hits one of two spots on that detecting screen. So the electron of that hydrogen atom is deflected in one of two directions, depending upon the direction of that electron spin. So jumping ahead of ourselves a little bit, if we have an orbital, and let's just say this is the s orbital, there's a rule that we'll talk about in a bit that says that only two electrons can occupy an orbital. And those electrons must be opposite in spin. So we've got one with a plus 1/2, one with a minus 1/2, so they cancel each other out. Otherwise, we would have a problem. We can't have two negatives or two positives in that orbital together. So opposite spins for those electrons. And I think next we're going to talk about how we write sets of quantum numbers and electron configurations and orbital diagrams.